A data center is, at its core, a large collection of computers connected to electricity, cooling equipment, storage systems, and high-speed networks. Moving those computers into space does not change what they need. It changes how every one of those needs must be supplied. The computers still require a continuous flow of electrical power. They still produce heat that must be removed. They still need to exchange enormous quantities of data, replace failed components, and protect stored information. On Earth, these tasks are difficult but routine. In orbit, each one becomes a separate engineering problem. The idea is attractive for several reasons. Solar panels in orbit can receive intense sunlight without clouds or most atmospheric losses. A space data center would not occupy valuable land, and it would not directly consume fresh water for evaporative cooling. It could also process information produced by satellites before transmitting only the useful results to Earth. But placing a data center in space does not automatically make it efficient. To find out whether the idea is practical, we need to examine the complete system, its orbit, power supply, cooling method, communication links, protection, maintenance, and eventual disposal. The first decision is where the data center should orbit. A low Earth orbit, or LEO, might place it a few hundred to roughly 2,000 kilometers above the planet. At these altitudes, communication delays can remain relatively small, and reaching the structure requires less energy than reaching a much higher orbit. However, the data center would travel around Earth approximately once every hour and a half, repeatedly moving between sunlight and Earth's shadow. A higher orbit could provide longer periods of sunlight and allow the data center to remain visible from a larger part of Earth, but it would be more difficult to reach, harder to repair, and exposed to a different radiation environment. Communication delay would also increase, because every signal must travel a greater distance. There is no perfect location. Lower orbits are more accessible, but experience atmospheric drag and greater congestion. Higher orbits reduce some of those problems while increasing others. The orbit must therefore be chosen for a particular type of data center, rather than for the general idea of computing in space. The next problem is power. Outside most of Earth's atmosphere, sunlight delivers approximately 1,361 watts of energy per square meter when a surface faces the sun directly. A solar panel converting 30% of that energy would ideally produce a little over 400 watts per square meter. Real arrays produce less after accounting for their angle, temperature, electrical losses, structural gaps, radiation damage, and gradual degradation. Suppose the computers alone require 1 megawatt of power. Even under highly favorable conditions, the solar array would need to cover several thousand square meters. The complete system would require even more power for networking, pumps, batteries, communication equipment, guidance systems, and onboard robotics. Solar panels would therefore be a major part of the structure. They might extend away from the computers as enormous wings, while motors continually adjust their direction toward the sun. A larger data center demanding tens or hundreds of megawatts would require correspondingly larger arrays, unless another source of energy were used. Power must also remain available when the data center enters Earth's shadow. In low orbit, this can happen during a significant part of every revolution around the planet. Batteries could store energy while the spacecraft is illuminated and release it during each eclipse, but batteries add mass, occupy space, produce heat, and eventually degrade. A carefully selected orbit could reduce the duration or frequency of these eclipses, although it would not remove every other difficulty. Nuclear power is another theoretical option for continuous electricity, but it introduces additional mass, heat, regulation, safety requirements, and launch concerns. For most early designs, large solar arrays combined with energy storage would be the more likely approach. Providing electricity is difficult. Removing the resulting heat may be even harder. It is easy to imagine space as an extremely cold environment that would naturally cool a computer. However, temperature and heat transfer are not the same thing. Space contains almost no surrounding matter, so there is no air to carry heat away through convection. On Earth, a server can transfer heat into moving air or circulating water. That warm material can then carry the energy toward cooling towers, chillers, or the outside environment. In a vacuum, a space data center cannot release its heat into nearby air because there is practically no air available. Nearly all the electricity consumed by a processor eventually becomes heat. A 1 megawatt computing system must therefore reject approximately 1 megawatt of thermal energy in addition to heat created by the rest of the spacecraft. The heat does not disappear simply because the machine is no longer on Earth. A space system must first conduct heat away from the processors. A liquid coolant could circulate through cold plates attached to the computer hardware, transporting energy toward large external radiators. Those radiators would then emit the energy as infrared radiation. The amount of heat a radiator can release depends strongly on its temperature. According to the Stefan-Boltzmann relationship, radiated power increases with the fourth power of absolute temperature. This means that a hotter radiator can reject much more energy per square meter, but computer components and coolant systems cannot operate at unlimited temperatures. At temperatures suitable for ordinary electronics, rejecting 1 megawatt of heat could require thousands of square meters of radiator surface. This is only an approximate scale, because the final area would depend on radiator temperature, material, orientation, and exposure to sunlight and radiation from Earth. NASA treats thermal control and high-power heat rejection as major spacecraft engineering capabilities for precisely this reason. The radiator and solar panels also compete with each other. The solar array should face the sun, while the radiator should generally avoid direct sunlight and face cold, open space. The structure may need long booms, rotating joints, sun shields, or separate modules to keep these surfaces properly oriented. This gives a space data center a very different shape from a building on Earth. Much of its visible area would not contain computers at all. It would consist of power-generating surfaces and heat-rejecting surfaces connected to a comparatively small central computing section. The computers themselves would also face a hostile environment. Earth's atmosphere and magnetic environment protect ground-based electronics from much of the high-energy radiation found in space. In orbit, energetic particles can pass through electronic components, disturb stored information, change individual bits, or permanently damage circuits. Please consider subscribing if you're enjoying the video so far. I'll be uploading many interesting videos regarding physics, tech, and chemistry. The severity of the problem depends greatly on the selected orbit. One solution is to use radiation-hardened processors, but these are usually designed for reliability rather than maximum computing performance. A data center built entirely from specialized space-grade chips could fall far behind the performance of modern terrestrial hardware. It could also become extremely expensive. Another approach would use more conventional processors with protective shielding and extensive fault correction. Important calculations could be performed more than once on separate machines, and the results could be compared. Error. Correcting memory could repair some corrupted information, while damaged servers could be isolated and restarted automatically. These protections would consume additional power and computing capacity. Shielding would also increase launch mass, and no practical shield could stop every highly energetic particle. A space data center would have to be designed with the assumption that failures will happen, rather than with the expectation that every component will remain perfect. Small particles create another danger. Natural micrometeoroids and fragments of old spacecraft can travel at several kilometers per second. At those speeds, even a tiny object can puncture a radiator pipe, damage a solar panel, or destroy exposed equipment. Spacecraft already use layered shielding to reduce this risk, but a data center would present an unusually large target. Its wide solar arrays and radiators would be difficult to protect completely. Individual sections would need isolation valves, redundant coolant paths, and enough spare capacity to continue operating after limited damage. NASA develops specialized shielding because micrometeoroids and orbital debris remain genuine threats to spacecraft hardware. The next major challenge is communication. A useful data center must receive information and return results. Radio links can perform this task, but a large computing facility might need far more bandwidth than an ordinary satellite. Optical communication systems can transmit information using narrow laser beams and potentially carry much more data than traditional radio links. Laser communication is already being demonstrated at very high data rates. However, the beam must be pointed with extreme accuracy, and clouds or atmospheric turbulence can interrupt a link between orbit and the ground. A reliable network might require several ground stations in different locations, allowing the system to select whichever station currently has clear weather. Bandwidth is only one part of the communication problem. Latency also matters. A signal traveling to low Earth orbit and back covers at least hundreds or thousands of kilometers, producing a delay of several milliseconds before processing time and network routing are included. That delay might be acceptable for video delivery, scientific calculations, or many artificial intelligence tasks, but it could be noticeable in applications requiring an almost immediate response. Higher orbits increase the delay further. For this reason, an orbital data center would probably not replace every nearby terrestrial data center. It would be better suited to workloads that tolerate some delay or that already originate in space. An Earth observation satellite, for example, can produce far more raw information than it can easily transmit. Instead of sending every image downward, it could forward its data to an orbital computing platform. The platform could identify clouds, fires, storms, ships, damaged infrastructure, or other relevant features, and then transmit a smaller set of results. This avoids sending unnecessary information through the atmosphere. It also gives a space data center a clear advantage that a ground facility does not have. It is already near the source of the data. Early orbital computing systems are therefore more likely to act as processing hubs for satellites than as complete replacements for ground-based cloud services. Launching the hardware creates another constraint. Servers on Earth are designed to fit into racks, not to survive intense vibration, acceleration, and acoustic pressure during a rocket launch. Every computer, cable, radiator panel, coolant pipe, and solar array would need to be strengthened, folded, or packaged for transportation. Strengthening the equipment adds mass, and launching mass requires energy and money. A single launch would probably not carry an enormous finished data center. A more practical design would use standardized modules launched separately and connected by robots in orbit. Power modules, radiator modules, computing modules, and communication modules could be assembled gradually, allowing the facility to expand over time. Modular construction would also make repairs more realistic. Instead of opening a server and replacing one small component, a robot could remove an entire failed computing unit and attach a replacement. NASA and other organizations are already developing technologies for robotic satellite inspection, refueling, repair, assembly, and upgrading, although operating a large data center would require these capabilities at a much greater scale. Maintenance is especially important because computing technology improves quickly. A processor that is advanced when launched may become inefficient compared with new ground hardware only a few years later. An economically useful orbital facility must therefore support frequent upgrades rather than remain permanently sealed. Failed and outdated modules would also need somewhere to go. They could be moved into a controlled disposal orbit, deliberately guided into the atmosphere, or possibly returned to Earth. Simply abandoning them would add more debris to an environment already shared by thousands of operating spacecraft. Low orbit structures experience a small amount of atmospheric drag. Over time, this reduces their altitude, so propulsion is required to maintain the desired orbit. A very large data center with broad panels would experience more drag than a compact satellite, and solar activity can expand Earth's upper atmosphere, increasing that drag further. The facility would therefore need engines, propellant, or some other method of orbit maintenance. It would also need to avoid collisions, control its orientation, and remain stable while large components move or dock with it. These systems consume still more mass and power without performing any actual computation. This does not mean that space data centers are impossible. None of the individual requirements violates known physics. Solar power, liquid cooling loops, radiators, radiation-resistant computing, optical communications, autonomous control, and robotic assembly all exist in some form today. The difficulty appears when they are combined at data center scale. A small experimental module may require kilowatts of power. A major terrestrial data center can require hundreds of megawatts. Scaling from the first level to the second does not merely mean adding more servers. It means adding enormous solar arrays, radiators, launch vehicles, batteries, communication terminals, propulsion systems, and replacement hardware. The environmental argument is also more complicated than it first appears. An orbital data center could avoid direct land use and water consumption at its operating location, but rockets, spacecraft manufacturing, ground stations, replacement launches, and disposal would still have environmental effects. A fair comparison would have to examine the complete life cycle rather than only the electricity used by the processors. For the near future, the most believable space data center is not a giant orbital copy of a terrestrial facility. It is a smaller, specialized computing station designed to process satellite information, support spacecraft, or perform work that does not need constant communication with Earth. Several such modules could eventually form a distributed orbital network. New processors could be delivered as replaceable units, while shared power, cooling, and communication systems serve the entire platform. This modular approach is close to the type of orbital data center infrastructure now being examined in European research programs and industry discussions. So, are space data centers possible? Technically, yes. The real uncertainty is not whether the computers can be made to work, but whether the complete system can compete with a building on Earth. For ordinary cloud storage, web services, and large artificial intelligence training clusters, terrestrial data centers currently have overwhelming advantages. They can connect directly to power grids and fiber networks, and technicians can repair or replace their hardware within hours. Space turns every routine maintenance task into a mission. For information already being generated in orbit, the balance is different. Processing the data near its source can reduce communication requirements, shorten decision times, and allow groups of satellites to share computing resources. In that specialized role, orbital data centers may be not only possible, but genuinely useful. The first space data centers will probably not resemble vast buildings floating above Earth. They will begin as compact, modular machines attached to satellites or orbital platforms. Their development will be gradual, with each generation testing larger power systems, larger radiators, faster communication links, and more capable robotic maintenance.